Hello everybody, and welcome back to another geometry lesson. Today we're taking a look at section 7.2, properties of parallelograms. Now, that's a shape that we probably haven't heard from a very long time, since around elementary school. So here's a quick refresher. A parallelogram is defined as a quadrilateral, so it has four sides. A quadrilateral whose opposite sides are parallel, hence parallelogram. So this definition is intentionally pretty loose. Parallelograms are a lot of different shapes. We just call them all parallelograms as a category. For instance, one example of a parallelogram is this. This is actually the most common example you will see, is a shape that looks like a slanted box. From what we can tell, these two sides, the ones on top and bottom, seem to be going parallel to each other. And from what we can tell, these two diagonal sides seem to be parallel to each other as well. It's a parallelogram. But what are some other shapes that fit that description? Any quadrilateral whose opposite sides are parallel? Some of you may have immediately thought of a rectangle, and you would be correct. A rectangle is a special type of parallelogram. In fact, you can even see the resemblance in this family. In a rectangle, once again, we have a pair of parallel lines there, and a pair of parallel lines there. It's a parallelogram. There is another shape that might fit this. There's a couple of them, but one is a square. You can't really call it a squarellelogram, so a parallelogram will have to do. Another shape that you will be seeing a little bit is a rhombus. For those who don't recall, a rhombus is a diamond shape. It looks very similar to our slanted parallelogram, except all the sides are also congruent. All the sides are the same length. So there are a lot of shapes that can be parallelograms, as long as they fit that description. This is just one facet of what makes something a parallelogram, is the opposite sides are parallel. There are a bunch of other properties that make parallelograms important. So the first one here is I'd like us to draw a parallelogram. I'd actually like us to draw a parallelogram, the same one, for all four spots here. So take a second to draw out parallelograms in each of the examples of these definitions. There we go. Not all exactly the same, but these are parallelograms. We're going to talk about some of the properties that these parallelograms share. And we're going to sort of use the names of the theorems as a hint. So here's a question. What else, other than the fact that they're parallel, do we think we can tell about the opposite sides of a parallelogram? Well, those who are keen-eyed among you may have noticed it seems like those sides are about the same length. This one's about 1 inch. This one's about 1 inch. Oh, the opposite sides of a parallelogram are congruent. So the top side and the bottom side will be congruent. The left side and the right side will be congruent. And this is always true of all parallelograms. The theorem goes like this. If a quadrilateral, which I'm going to abbreviate as quad, I don't want to write that every time, is a parallelogram, again, I'm not writing parallelogram every time because we're going to be writing it quite a few times this lesson, so I use a parallelogram symbol. If a quadrilateral is a parallelogram, then its opposite sides are congruent. They have to be the same length. So what do you think we can tell about the opposite angles of a parallelogram? Well, it seems like if I'm comparing these angles, this angle up here and this angle up here, they're opposite because they're across the shape from each other, not adjacent. They look to be the same measurement. Same with these two. It turns out that just like the sides, the opposite angles of a parallelogram are also congruent. So, if a quadrilateral is a parallelogram, then its opposite angles are also congruent. Cool. So I want us to pause here and take a look at example 1. In part A, it says solve for each missing variable in the parallelogram. We have a parallelogram here. They're telling us it's a parallelogram. So what do we know about these sides? Well, we know for a fact that this bottom and this top one are going to be congruent. We know that this left one and this right one are going to be congruent. So we can use that to solve for x and y. Y should be 15 because it's congruent with the side that's 15. X should be 9 for a similar reason. So what I'd like you to try is I'd like you to try all of these 6 problems in order to see if you can do it. I will say, even though they get a little bit trickier, this is around as difficult as they get. They might get a little bit tougher with setting up equations, but this is about it when it comes to those theorems. So pause the video, try them out. It should not take you very long. How did we do? These are all the answers for all of these variables. And we solved them by using the fact that opposite sides and opposite angles are congruent. Cool. Let's talk about these last 2 theorems. So in order to talk about the parallelogram consecutive angles theorem, I'm actually going to take a piece of paper here, and I'm going to draw a new parallelogram just to show you. You don't need to write this down necessarily. So I've got a parallelogram that looks like this. It's a pretty perfect parallelogram if I say so myself. And let's say that I knew that this angle measure here was, let's call it 100 degrees. Sure. Well, we would know that the opposite angle also has to be 100 degrees. Cool, cool. But what about these other 2 angles? There's a couple of ways to solve it. We could do it mathematically, we could do it geometrically. I mean, geometrically is mathematically, but I mean algebraically or geometrically. Geometrically, we know that a parallelogram is made up of parallel sides, right? So we actually know that we can do something with these parallel sides. If I extended out the sides here using dotted lines, this is what one side of a parallelogram would look like. And again, these entire lines are parallel to each other. What we've created here is a transversal that cuts through 2 parallel lines. So we know that this angle here and this angle here are consecutive. Consecutive interior angles add up to make 180 degrees. If this is 100, this one has to be 80. Geometrically, we could also, algebraically, we could also say, since all quadrilaterals add up to 360 degrees, remember that was the corollary to the polygon sum theorem. If we know that it's going to add to 360, and we know that 2 of the angles are 100, we can set up something like this. These are 200 together, plus 2x equals 360. If we subtract 200, we get 160. And if we divide by 2, 160 divided by 2 is 80. So no matter what, we get these angles. This means that in a parallelogram, any two consecutive angles, any two angles that are right next to each other, are supplementary. They add to make 180 degrees. The wording of the theorem is as follows. If a quadrilateral is a parallelogram, then its consecutive angles are supplementary. Cool, cool. Last and most certainly not least, we have a theorem regarding a parallelogram's diagonals. As a brief reminder, the diagonals of a parallelogram are found like so. These are what cut across from one vertex to another. The fun thing about these, though, is that they actually cut each other in half. What we've sort of found here is the middle of the parallelogram, right? That means that if this point here is the middle of the parallelogram, then those two sides of the middle have to be congruent, and these two sides of the middle have to be congruent. If a quadrilateral is a parallelogram, it means both of those things. It means that those diagonals cut each other in half. If a quadrilateral is a parallelogram, then its diagonals bisect each other, meaning they cut each other in half. Beautiful. Let's take a look at the back page. So here we've got a couple of different types of examples, and of course, we're starting off with a proof. It's been a while since we've had one of these, so let's take a look. We are told that this left figure is a parallelogram, shocker, I know, and this right figure is a parallelogram. We're trying to prove that angles B and F are congruent, which I'm just going to color over in purple here. And somehow we're supposed to figure out that those two angles are the same. Well, first things first, what do we do with all proofs? We've got to write down our givens. So A, B, C, D, and G, D, E, F are parallelograms. So, and we know that we're going to eventually prove this. But for right now, we're going to write down that these are given. And that's it. That's all we're told. And we somehow have to prove those two angles are the same. Ridiculous, right? A hint that we always give is to look at the diagram when you're not given a lot of information. Are there any angles in this diagram that we know are going to be the same? Because I spot some over here by point D. This angle here on the left, angle CDA, is congruent to this angle here on the right, GDE. So angle CDA is the same as angle GDE, but why? Because they're vertical from each other. That's what the vertical angles congruence theorem tells us. Vertical angles are congruent. But wait a second. There's something else that we know from this too. In a parallelogram, the opposite angles are congruent. So that means CDA is also congruent to angle B, right? So angle B has to be congruent to CDA. And we can do the same thing on the other side too. Angle F has to be congruent to GDE. angle GDE is congruent to angle F. What theorem is that that says that the opposite angles of a parallelogram are congruent? Well, it's we mathematicians not being very creative with words again. It's the parallelogram opposite angles theorem. Some of you may have noticed that we now have enough energy to put this together. B is congruent to CDA. That's a fact. But CDA is congruent to GDE. But GDE is congruent to F. We've made a chain of things that are congruent to each other, reaching from one end of the shape to the other. Because of that, we can cut the middleman and just say angle B is congruent to angle F. What theory is it that says we can chain different congruency statements again? It's the transitive property of angle congruence. Done. Simple as that. Let's take a look at example 3. Example 3 is solve for the missing variables in each parallelogram. This is just like example 1, just using the diagonals theorem and consecutive interior angles theorem. For letter A, we know that the two consecutive angles of a parallelogram have to add to 180. So we can say 70 plus n has to be 180. Means n is 110. That's part of our answer. N and 2m are next to each other, so those are supplementary. So 2m plus 110 has to equal 180. We subtract 110 from both sides. We get 2m equals 70, or m equals 35. So pause the video once more. Let's see if we can try out B and C on our own. How do we do? M is 8, K is 7, U is 4, V is 18. Perfect. The next example asks us to find the coordinates of the intersection of the diagonals of the given parallelogram. What does that even mean? Well, recall when we did this definition here, I put a dot right in the middle and said that's the middle of the parallelogram. This is what it's actually asking us to find, the middle of the parallelogram. Now, there's two main ways to do this. There is a bit of a longer way that involves us graphing, and a bit of a shorter way. I'm going to do both here with A and B. So let's take a look. Let's start by graphing part A. So we've got L at 1, 4, M at 7, 4, N at 6, 0, O at 0, 0. We've got our parallelogram. Perfect. Swoosh, 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 and swoosh. Right? To find the intersection of the diagonals of these shapes, I'm going to draw these diagonals, let's draw them in red actually, across the shape. And we're trying to figure out the coordinates of that spot. But we know something about the coordinates of this spot. It's the midpoint between any two opposite vertices. So if we can find the midpoint of L and N, for instance, we've got our intersection. Recall the midpoint formula is found by adding together your x values and dividing by 2, adding together your y values and dividing by 2. So we could just plug in. This is method 1, is plugging into the midpoint formula 2 of the diagonals. So we get 1 plus 6 divided by 2, 4 plus 0 divided by 2. The coordinates of m are 7/2, comma 2, which is around 3.5 for 7/2. It's not around, it's exactly 3.5. What if I don't give you a graph, though? The problem is, if I don't give you a graph, you would not be able to tell which two corners are diagonal from each other. I could have scrambled these points all around. We would have no idea which two corners are opposite from each other. So allow me to offer you an alternative. I'm going to give you an unrelated seeming problem that will soon be apparent how related it is. Let's say last semester I took 3 tests. On the first one, I got a 72%. On the second one, I got a 90%. And on the third one, I got an 84%. Cool. How could I figure out the average of my tests? Well, recall that an average is found by adding together all of your data points. So sum of data divided by the number of data points you have. So in this case, we could do 72 plus 90 plus 84 divided by 3, because there are 3 points, and we would get our average. In this case, the average of these 3 numbers ends up being 82%. But this idea of an average works on geometric figures as well, because the average is just another way of saying the middle. Anytime you're trying to find the middle of something, you can add up all your data points and divide by how many you added. So without graphing this at all, we can use a different method. Actually, let me scribble these out. I don't want you to think these are diagonals. A different method would be to add together all of your x's, in this case 4 of them, and then divide by how many you put together, so 4 of them, and do the same for your y's. So x is going to be negative 2 plus 4 plus 0 divided by 4. Y is going to be 5 plus 0 plus 0 divided by 4. Our point is going to be 4 divided by 4, which is 1, 10 divided by 4, which is 5/2. A little bit easier, right? And there's the difference. All right, folks, last problem, and then we are done. This last problem is one where you are technically able to solve it without using a graph, but I don't recommend it for reasons we're going to discuss in a moment. So, we know 3 vertices of w, x, y, z. Only 3 of them. We don't have the 4th. We have the coordinates here, which we can graph, and we're asked to find the coordinates of vertex y. Overall, we have the data to do it, but it's going to be a bit tricky. Here, let's graph it first and see what we get. So I'm going to graph w is at -1, -3. X is at -3, 2. Z is at 4, -4. So this one's w, this one's x, and this one is z. Some of you may be visualizing what this parallelogram looks like, which is great. But I wish to inform you, there's more than one possibility. Let me show you an example. Let's say I've got, if you're visualizing it just based off this, there'd be multiple possibilities. Let's say this is all you had. Let's say you just had these 3 points labeled out. We know that a quadrilateral has to have parallel sides, so they have to look the same, and congruent sides. They've got to be around the same distance. Maybe some of you thought your parallelogram would look like this. These 4 points. And you'd be reasonable for thinking that. But this is not the only option. For instance, what if this was a side and the parallelogram went down like this? What I mean is, what if it looked like so, with these dotted lines here? Well, that'd be a little bit trickier to find, right? That's still a parallelogram, though. It's just a long one. Okay, what if the dot was actually over on this side? What if it was all the way over here? We'd have an even longer parallelogram. So ultimately, we don't actually know which one the parallelogram is if it wasn't for one detail. We are told that the parallelogram's name is WXYZ, which means the points have to go in order alphabetically, W to X to Y to Z. So if I start at W here and go to X, there is no way for me to go over here to find point Y. We have to cross over itself. It looks like an hourglass. Same with down here. The only way for us to have point Y is if point Y is somewhere around here, somewhere in this big box here. But how do we find it? Well, the best way to find it is to use the slopes. Recall that parallelograms' opposite slopes, that their opposite sides are parallel. And parallel slopes are the same. So we can find the slope between x and w, or w and x, and use it to find the slope between y and z, or z and y. To find the slope of wx, we go from w and check our rise and run. So 1, 2, 3, 4, 5, and over to the left 2. Going up is a positive direction, going left is negative. Our slope is just -5/2. So we can do the same to go from z to y. To go from z to y, we just repeat the directions. 1, 2, 3, 4, 5, left 2. That is where point y should be. Again, the slope will have to be the same, so y is at the coordinates 2, 1. That's what makes it a parallelogram. So you can always use the slopes to find missing points. The one thing I'd like to mention with this is you can also do this in your head. The graph helps us visualize where the points are, but if you are really good at visualizing generally where points are in a space, you can sort of see what this parallelogram is going to look like. W is in the negative quadrant. X is going to be in quadrant 2. Z is going to be over here in quadrant 4. So we know that y has to be up here, and we can just find the slopes mathematically as well by doing y2 minus y1 over x2 minus x1. I don't recommend this. This is not for the faint of heart. I do recommend graphing, and you will have a graph on your test. With that said, everybody, that is the end of our notes for today. Thank you so much for listening in, and have a great rest of your day.